So thank you. So I will present briefly the project of my IA chair called BisCottE. It's a very tortured acronym for Bridging Statistical and Computational Efficiency in AI. So I will present the goals in a minute. So let me say that this chair project is also in collaboration with several colleagues from my institute, the Institute of Mathematics in Orsay, and also other collaborators. So some of them also have actually AI chairs. So the collaborating colleagues at the Mathematics Institute are Sylvain Allo, Lénaïque Chiza, Elisabeth Gassia, and Christophe Giraud, who all work in statistics or in relation to statistics, and they have at least a strong interest in statistical learning. And I will also mention Frédéric Chazal, who is also presenting today from Université Paris-Saclay, and Rémi Gribonval, also from Université Lyon, who also happens to have an IA chair. And I listed some doctoral candidates that are either directly involved in the project or have a strong relation to the project to the left of the screen. So what are the the goals of this project? So as the title indicates, the high level goals are positioned into a theoretical analysis of some trends in machine learning and artificial intelligence related to statistical and computational trade-offs, which is a kind of a multifaceted issue that has been tackled from the point of view of theory, also as first heuristically, but also from point of view of theoretical guarantees, since at least there is a strong interest in that, these kind of teams in the last 10 years, I would say at least. So what does it mean to be efficient? So roughly speaking, there are several kinds of efficiency you can talk about. The first one is maybe the most classical one is label efficiency or statistical efficiency, or you can say also efficiency in an information theoretical sense, which means that you want to extract as much information as you can from your available data. And in traditional statistics, it means getting convergence rates at the number of examples or label examples increases. Or in machine learning terms, how many examples do you need to reach a statistical guarantee at a given level? Now, this is shifting to other questions like online efficiency. In particular, questions like requesting only just the right amount of data as needed for whatever task is at hand. So not plan a priori, but kind of optional stopping depending on how hard is your task, and discovering the hardness of the task as you go. And another kind of interesting issue is sometimes called the small data problem. So after big data, you also have some small data tasks with small data. In that case, an interesting problem is that you have many tasks to solve, or many problems, for each of which you have a small amount of data, and the question is whether you can take advantage of the fact that you have multiple databases for related tasks to gain information efficiency. The second point is computational or resource efficiency, which is of course related to traditional computation complexity theory. So it's a point of view of computer science. For a long time, I would say that label efficiency and computational efficiency have been like two, not talking to each other, but it has been different in the last 10 years. So of course, for computational efficiency, the main two criteria are computation time, so algorithmic complexity, if you will, and also memory efficiency, which is directly linked. And so the interaction between the two, for example, between the two first kind of efficiencies, are illustrated in methods where you were interested in early stopping. For example, early stopping in approximation or optimization steps, where you need to reach the right amount of approximation or optimization. So you don't need to optimize it until the end in order to get a suitable approximation for whatever problem you have at hand. And finally, I will also mention a third kind of efficiency, which I call structural efficiency, which is also, in a sense, also known under several forms before. So here it's taking advantage of the unknown structure in data. Some to be more efficient, either computationally or in a statistical sense. So one example is if the data lies close to an unknown manifold, and you want to take this structure into account, even though you don't know it. And another trend is to find is the whole trend of finding efficient representation for data, for example, sparse representation, but there are others in which you can gain efficiency both from the point of view of data compression, data representation, but also from the statistical sense. So in some sense, the questions are also the interaction between these different kind of efficiencies. So if you want to have an algorithm that is statistically efficient, you can, as a statistician, I can devise, so this is where I come from, devise a method that in theory will be like minimax efficient. So you cannot do better in a certain sense, statistically speaking. But then someone comes and says, yes, but it's impossible to implement. So if you try to introduce some additional approximations and that allow to be more efficient, do you lose from the, or how you can do that to be sure that you won't lose from the point of view of statistical efficiency? So, and hence this idea of trade-offs. So there are many instances or incarnations of this kind of questions. This is, as I mentioned, this is a mainly theoretical orientation of the project, but I welcome interactions with other projects. So if you're interested in interacting or trying out some ideas on data, it's absolutely welcome, and I welcome any interactions. So for the rest, I decided. Excuse me, there is Larsen. Yes. Sorry, hi. You can hear me? I cannot hear you. Yes, yeah. Okay. Okay. So for the rest, I had planned to present briefly two ongoing projects in broad terms to give you an example of what I mean, this is very high level. So what concretely kind of project that students are considering. So the first one is with El Medisad, currently a PhD, and it's about efficient variable selection. So here we consider a very traditional linear regression problem, which is still the bread and butter of statistics, but also in learning. So imagine you have a ID data, and the model, the label is a linear function of xi plus noise. So a very old problem in statistics actually is to try to find the support of the vector beta star, especially if you're on high dimension D. Assume the support of the true vector, so the number of covariates that are actually relevant for your problem is kind of small with respect to D, and you want to ideally would like to find the support of beta star. So independently of the problem itself, if you can reduce your attention to a certain set of covariates, then you can reduce the dimension, and it's much more efficient after that. So of course there exists a large number of methods. This is an old problem. There are forward methods. There are in statistics. There are lasso is an example that is very much used now also to try to find variable selection. So here we have concentrated from this efficiency idea on a very traditional and or widely used method, which is orthogonal matching pursuit, which you probably know already. So to sum up very quickly, how does orthogonal matching pursuit work? It's a forward method. So it selects one coordinate or one covariate after another. And the way it works is you start with an empty vector. You calculate the residuals. So the first step, the residuals are just the labels themselves. But after that, you will take residuals with respect to the current vector beta. And then you just compute empirically the correlation or the empirical correlation between the residuals of the labels and each coordinate of the regression vector. And you take the maximum correlation. This is the maximum correlation is your next selected variable. You add it to the current support estimation. And finally, that's the orthogonal part. You do an orthogonal least square regression, but restricted to the current support you have selected. This gives you your new vector beta bar, and then you iterate, you calculate new residuals, etc. So it's a very simple procedure in a sense, so that's why it's very popular. And it has been studied theoretically, or like when does it effectively select the true, correct covariates? This has been studied from a learning theoretical sense only quite recently, I would say like 10 years ago, in particular by Zhang. I mean, there are many articles related to this method, but I think the one that I like is a study by Zhang, and in particular under certain assumptions, it says how many examples you need n to reach a consistent variable selection. So this is a purely batch method in the sense that you have n data which are given to you, and then if you follow Zhang's theory, n has to be big enough, and given that n is big enough, you just do this. So a question is, how can you be more efficient, but still have a version that is more efficient of this algorithm? And so in particular, if you look at the different steps I described, the complexity is big O of k, the number of steps of selection steps, times n, the number of examples, times d. And remember that n actually has to be big enough, depending on some parameters that I don't specify here. And the approach of LMAD is to try to have an online version of such an algorithm, in which at each selection step you only request in an online manner as many examples as you need, and so it mixes an approach linked to bandit, let's say bandit style theory to try to select, so the coordinates become arms. You try to select a correct arm for which, or a correct coordinate for which you can ensure it is in the support, and then iterate. So it requires to have also an online version of the ordinary least square steps. So everything becomes online, and we have two models for this online. One is just completely online in a data stream model, where you ask examples or like subsets of examples, such as subsets in the sense that you can ask for certain coordinates only. And this is of course less computationally demanding. But then you can look back. You cannot ask back for a data point about the coordinates. So a database model, suppose you have a huge database, you can query any element, any coordinate in the database at any point, and any query for one particular coordinate of one particular point costs you a unit cost. Okay, and basically, so it's able to show that under similar situations as in Zhang, this approach actually can gain substantially computational advantage. So my question is, how much time do I have? Because I don't know if I started at, have I already been up to 15 minutes? Okay, so I will just maybe sketch just the problem of the other ones I wanted to sketch to give an example. So this is an example of a very like prototypical example of a small data problem, and here the problem is very simple. It's mean estimation. So imagine you have several means to estimate. It's the simplest you can think of in a sense. You have several samples. Each sample is from a separate distribution, P index B, and you have several distributions from B equals 1 to large B. And for each of these distributions, you have a sample of size n. So the means are different. For each mean, you have a certain amount of data, and the question is, okay, so you can of course estimate each mean separately, just by taking, let's say, an empirical average, the most naive estimator, separately. The question is, can you take advantage of the fact that you have many samples and many means somehow to improve the estimation of the means. So this seems a very theoretical statistical problem, but in fact, it is motivated by machine learning applications, in particular in relation to kernel mean embedding, KME methodology, methodology in which you represent whole distributions by vector and Hilbert spaces using kernel methods, and basically by taking the expectation of a certain feature mapping phi of p that you replace by an empirical distribution. And this has many, many applications, as you maybe already know in machine learning. So here the question is that if we can improve mean estimation, actually this would be, in particular in high dimension, this would be very beneficial for estimating simultaneously many KMEs. And this is a question that has already been considered by authors, in particular in this kernel setting. So I give a few references. And here, so let's say I won't talk more about the method, but we suggest a very simple method where you tend to aggregate together some data sets for which you test if the means appear to be close enough. So if you aggregate several data sets, you can hope to reduce the variance if you average over different independent data sets. Of course, you introduce bias because the means are different, but if you have a good test that allows you to detect whether the means are close enough, it turns out that you can actually improve up to a certain level. And just want to mention in the last slide that this improvement is actually theoretically the most important when you are in high dimension. So it is actually a phenomenon of where you have a kind of you have a curse of dimensionality, because in high dimension it's harder to estimate anything, in particular means. But it turns out that you also can then take more advantage of this similarity between means to reduce variance. So there is also a phenomenon of blessing of dimensionality that appears, which I think is interesting and maybe potentially very interesting for applications. Thank you. So I will stop now.
Put back the mic on. So is there any question from the audience? So I prepared actually one question, Gilles. Can you explain a bit the interactions with the team and how you organize the different projects with the different people that you mentioned around in Paris-Saclay, who you see involved in which aspect, and to see how the project is organized?
So for the moment, I mean there are some projects are kind of separate. And we have, I have basically just started. So the idea is to have inside the laboratory of mathematics a group working on related issues and statistical machine learning. It is also interacting with an existing INRIA team. And so in practice, we want to have also probably a group seminar starting this year. So of course the Corona situation has not made this very simple. But let's say that okay, at this point we have several separate projects, because this is maybe more the nature of theoretical investigations and mathematics, that you have a well-defined project and that everybody works on his problem. But in particular, so what I mentioned is that concerning, for example, the second project, so I have two PhD students working on different aspects of it. One of them is actually in Berlin, at the TU Berlin, and in the laboratory of Klaus Robert Müller. But okay, so I don't know if there is anything else to say about the organization.
Okay, thank you very much, Gilles. Any burning question from the audience? Yes, Bertrand, and maybe Jean-Christophe, if you're here. Yes, if you can start to set up before, so we don't go too late. Bertrand. Did you hear?
Okay, so for the moment, for example, I So one idea, for example, for the project on OMP would be to have at least a demonstration toolbox. I mean, LMEDSAD is actually doing some experiments on toy data using a database model, but of course, to scale it on real data, I think it would be necessary to also interact with real problems. So for the moment, let's say we don't have as an immediate plan to have a general purpose box, but given the interest, I mean, but definitely would have like at least a proof of concept software that we want to publish, and then it also depends on future interactions, I would say.
Okay. Thank you very much, Gilles.